morning, everyone. So this is a talk on extracting meaning from text. Okay, fabulous. So I'm going to give you an entry-level talk, so it's not going to be super technical here, on text analytics and how we can go about extracting meaning and interesting things from the text that we have around. The necessary starter slides, picture of me in case you can't see me. I'm a data scientist, I work at the Bank of England. I started off as an economist, kind of converted through computer things into data science. A quick plug, if any of you are interested in data science and data scientists and growing your own, there is a new standard for data science apprenticeship, so anyone whose company either is subject to the apprenticeship levy or just fancies growing some data science apprentices, take a look at this link, and it's got a whole range of sort of competencies for data scientists, and these are courses now being established by universities as of this September and going forward. So that's the plug over. So what we're going to talk about today, we're going to talk about analysing text and the challenges we have doing it. We're going to talk about using computers to work out the meanings of words. We're going to have a little introduction to something called word embedding, which some of you will have heard of, some of you will not. How we can take these sort of numerical representations of words and do things with them, and then we'll have some examples, some of them more realistic than others. Okay, so there's loads of text these days. We have access to lots and lots of it. Everything is digitized. We have archives of historic text. We have reams and reams of new text coming through online sources. So, brilliant. We love data here, that's why we're here. So how can we analyse that? Text is fiddly and text is complicated. So, for the first point, vocabulary. A varied vocabulary is brilliant. Makes things super interesting, and it's really annoying. So, if you're trying to extract meaning, we would love it if there were no synonyms, there were no idioms, there were no turns of phrase, there were no different ways, there were no homonyms, single word that mean different things. That would be fantastic, but that's not what we've got. So it's annoying, it's frustrating, it's galling, it's irritating. There's all the things. I love crosswords, so these things are fabulous, but they're really annoying when you're trying to do your actual work. So, when we're talking about analysing text, what is it we're really trying to say? We're trying to summarise, we're trying to find insight. So what is that we're trying to find out? We could just be counting the number of times somebody says Tesco's, if we work for Tesco's, and that's great. That's also not very difficult. Oftentimes we're trying to do something a little bit more nebulous. So that might be extracting topics. So what is this person talking about when they're talking? What are they actually saying? And determining sentiment. So sentiment is quite a broad phrase here. It's almost the how. How are they saying it? Are they dry and factual? Are they excited? Are they disappointed? Are they angry? This is the kind of thing we might be trying to extract from our text sources. So, can we use tools to do this? And can we nail down some specifics within that? Topic extraction is a whole other theme. I'm not going to talk about it here, but there are techniques for finding the topics within text. But can we do some of these other little tasks? Finding synonyms, so that list of words for annoying. Or can I actually get a hold of that? Can I start with annoying and find other things that are similar to it? Can I see how language changes over time? How the meaning of web or net has changed from 50 years ago to today. And can I, in a more broad sense, turn my text into numbers and then do things with them? I guess you're hoping the answer is yes, otherwise it's going to be quite a short talk. So yes, we can, yes. So we're talking about the essence, we're talking about word meanings here. And to get meaning, we need context. So You can probably see where this one's going, right? Python is my favourite what?
Steak.
I went reptiles, but yes, good. Or programming language, right? So, you know, these are one perfectly normal sentence. I can't tell what Python means in this sentence until I have the last bit. I don't know what kind of Python I'm talking about until I've got that last bit. So we know a word by the company it keeps. And this is the concept behind something called word embedding, and this is what we're going to talk about today. Some examples of this are word2vec. This one's been around a few years. Fast text, this is a more recent one. I hope the next one will become like really fast text. There's another one called glove. There are a variety of these different models, and what they're aiming to do is turn text into a numeric vector, which is effectively a score of the context and a score of the meaning. And this is where we're going to start to lose people a little bit. So, what do I mean by vectors? And vectors as regards text. Hands up who even knows what a vector is. Good. Most people. This is a good thing. So, I'm going super technical here. We're talking about thingness. So, to get to the meaning of a word, we're trying to encode the characteristics of it. So, you can think of our Python example. If we're talking about the snake one, you can think of characteristics that snakes have. And for any word, we can therefore take a list of those characteristics and then score them. So I'm going to take a bunch of words and I'm going to score them against a set of characteristics. So here's an example. Let's take pets. So we might score them on size. It's ironically quite small text. We might score them on furriness or friendliness or whether they like to go for a walk. Okay, so that's great. And there's a bunch more things that we might do that. And if we put enough of those in there, we can probably uniquely define each of our possible pets based on the characteristics that they have. And once we take those scores, we put those scores together, that's a vector. So a line of figures, each of which represents something. So I've scored hamster there. Not very big, very furry, pretty friendly, not that keen on going for a walk with you. They're quite keen on walking, I think. The next thing we can do then, I've scored hamster, I'm going to score some other things. And when I've gone and scored some other things, I can compare them. And then we can, intuitively for pets, we have an idea of which ones are going to be closer to each other than others. So, what's this? Gerbil, good. Hamster, quite close to gerbil. The vectors, we'd expect them to be pretty similar, right? One might be slightly furrier than the other, one has a longer tail, they're both quite sort of cute with short arms. Compare it to a python, or specifically a python eating a deer. Those we'd expect to be further away, less furry, less cute. Probably even less likely to go for a walk, actually, given the legs thing. Actually, yeah, that picture, that is a 31.5 pound snake eating a 35 pound fawn. So, if you go out for a big meal, is it like 1 and a bit times as big as you? So, we've created our list of all these vectors now. So for each pet, we've scored it. This is great if it's pets, because we can kind of intuitively do this. We can set up the categories, and we can set up the scores. There could be lots of concepts. But now we're going to talk and take a step back, and we're going to go, right, words. Words in a document, words on a web page, the words in this presentation. Can you please choose some categories and score all of the words in a nice, consistent fashion? Anybody fancy doing that? No. So, happy days, they can be learned. You know what this thing is, right? So, because this is learning, we don't even need to feed the categories in. So this is unsupervised style of learning. So we're not going to start with a set of things and say score them against various. Score these words against power, or against argumentativeness, or against nouniness or adjectiviness. We're not going to feed those in. We're just going to say, off you go, create some categories and score them such that I get some different vectors for every single word, and with comparability. So I'm not going to know that out of my 300 characteristics, say, one of them's furriness. I might be able to work it out, I might be able to back it out, that actually these are the things that gerbils and hamsters score highly on and snakes don't. But we're just going to let the machine go and do its thing. And this is where word2vec, fast text, these kind of things kick in. So, a little bit more technical now. So, two-layer neural net takes in a corpus of text. So, your massive pile of documents, chuck that in, and it gives out that grid that we saw. Set of characteristics across the top, set of each of your documents, or specifically words in this case, down the side, and a score for each one. So we'll be able to get similar scores out for similar things. So Python might be close to Java, because Python's a programming language, Java's a programming language. Python might be close to Boa, because Python's a snake, Boa's a snake. So you might have, probably Java won't be anywhere near Boa in those terms, but they'll share some common characteristics across to Python. A quick note, word2vec is not the first of these things. So people have been thinking about this word embedding, this word vectorization for a long, long time. The big game here was actually the speed. So it's actually about being able to chuck absolutely loads of text in and get these numbers out in a reasonable time. We've talked about a couple of others that are worth going and having a look up. I'll mention a little bit about fast text later and just what the differences are. So I've talked a bit about this. Why do I actually care? Why do I want these numbers at the end? What's the point? So firstly, if I've got a model like this, I can consume lots of stuff. So I can consume vast reams of the internet, or my company's entire stack of documents, or responses to all the surveys that you've ever done. So you can bring them in, and so that's a practical, really useful thing if I want to pre-train them. And then the stuff we can do. So the point of these models is that they can learn concepts that are familiar to us, and that allows us to do really interesting transitions, and it allows us to do things like finding synonyms, finding associated words, all this kind of stuff that could be really useful for actually working out what people are talking about. And they can do it in a consistent manner, and this starts to be neat. So we can start playing word association games. So it can learn plurals, for example. One would argue these ones are not too hard. Cats is to cats, as houses to houses. So if you're about to do these kind of comprehension tests, these things can do them for you. You can learn synonyms, or approximate synonyms. So because it's pulling out these characteristics of how words are used, it can spot that an apartment may be the same as a flat, depending on which country you're in, versus a condo, which is not quite the same thing, versus a masonette, which is again not quite the same thing, but they all share a bunch of characteristics, and it can pull those out. And more importantly, it can find relationships that we haven't thought about either. So these relationships we know about, plurals, we know about synonyms. It might catch us things that are related and we had never thought about the relationship. Maybe we can see it afterwards. When we're talking about vectors and mathematical things, then we can think about plotting. And maybe that's a way to visualize that you can end up with a cat here and cats there, dog here and dogs there. And the point is that the pluralness can have a direction and a distance that will be consistent across words. So then if I plotted sheep over here, I could have sheep over here. That doesn't work out so well. Gerbil, over here and gerbils over here, and we'll get that same distance, or approximately same distance, for the plural nature of the relationship. If anyone has seen things about word2vec before, this is the classic example. So this is how we can do the maths. So I have a vector that represents the word king. I have a vector that represents the word man. And I take that away, so I'm sort of taking away manness. I add on the vector representing woman. So I've taken away manness, added womanness. What do I get? Spot on. And in fact, you can almost think of this in a couple of ways, right? We've got manness, male, femaleness, and we've got royalness as well, actually. So I could flip that round the other way. And there's the sort of king-man relationship and the woman-queen relationship. So because I've got these vectors, I can start getting this consistent direction and length. So let's go and see some of the examples that were in the original paper. They fed in a bunch of relationships. So France is to Paris. Microsoft and Windows, copper to CU. And I don't know how well you can see these, but it's mainly pretty good. So France is to Paris as Italy is to Rome. Great, capital city. Japan is to Tokyo, Florida is to Tallahassee. I think that is right. It's not always right. So Microsoft is to Steve Ballmer, Apple is to Steve Jobs, Google is to Yahoo. That's not quite right. The uranium chemical symbol hasn't come out, but the hit rate's pretty decent. And we can ask these kind of A's to B, C's to D. We can also do some adding up, and we'll show a bit of this in a moment. Finding synonyms and abbreviations in phrases, this is super useful. So if you've got text and you're not completely familiar with the full domain, then being able to feed in words that you do know and find the representatives that you never knew people were using, this is really useful for other text tasks. So, for example, finding how excited people are about it. Well, actually, what words do people use when they are excited? I don't need to, in advance, work out all those words. I can use something like this to help me out, to effectively go and say, well, what else do people say when they're excited? Basically, this stuff is hard. Context is hard to work out what people are talking about. So anything we can do to make it a little bit easier, that's fantastic. I'm going to show you a little bit of code and things like that. How can I do this? If I'm in R or in Python, there's a package for that. So there's one specific one called word vectors, another one called text2vec, one called gensim in Python. There are others now as well. These are generally wrappers for an original implementation. And the way I do this is I go and grab those packages. Then I have two options. I can either train my own model by feeding in loads of text, going and have a cup of tea or quite a lot of cup of teas, depending on how much text I fed in, and then wait to get the vectors out. Or I can use a bunch of pre-trained vectors, and the interweb will provide. There's plenty out there, and there are plenty of really big and interesting vectors ones. So for example, there's ones for Google News. It's quite broad ranging, it's got a bunch of things in. Massive quantities of Wikipedia or Twitter output. All of these kind of things. So if you don't need to train your own model, don't bother. If what you want to do is just find the relationships, find the outputs, then just use one that already exists. If you're using one that already exists, you need to know what it is. And you need to know what the downsides are going to be. There are some hopefully obvious ones. If you choose a source that doesn't ever talk about the technical stuff that you're interested in, it's not magic. It's not going to give you information if you haven't fed any in. Particularly things like US versus UK or other international things. If I'm really interested in flats, as in block of flats, if I use an American corpus, I'm not going to get anything, because I'm going to get flat tires or other flat things, and they're not going to be apartments. So I just need to know about this. So that's a sort of caveat over. So I am going to show some code. If you don't understand the code, don't worry. This will be in R. I hope it's mostly fairly self-explanatory because there's really not very much of it. So this is basically it. So the first one, go and get my package and load it up, where that path is somewhere off the internet that you downloaded it, or it's cram for R. Can't remember if these are cram, I think they are. The next one, this is me not training the model, this is me using an existing model that's been trained already. So this one, as the name suggests, is from Google News. It uses 300 categories to classify the words. And in this case, I've just taken the top 100,000. So it helpfully ranks them all in order of frequency. So that would be the 100,000 most frequent words that I'm going to get back. There's a trade-off here. I could take more. It's going to take me longer to load. I need a bit more memory. It's going to take me a bit longer to process, but I will pick up the rarer words. So this is kind of up to you to play around with and work out what you do. If you want to train your own model, that slots in that slot there. If you want to use a pre-trained model, this is how we do it. So I've loaded my library. I've read in my set of vectors. Now I can start doing some queries. So I've got two kinds of query here, all using this closest to function. One is just find me the words that are near this one word that I've provided. The next is, let's do some of this word association. So we've got a few addings and subtractings here, and we'll see how those work out. So, asking for some sort of big data, techie, linguistic-y kind of things. So, if I chuck in Hadoop, what do I get back out? It's pretty good. I've got some databasey things, some grid computing things. So, that's not unreasonable, these kind of words. If I chuck in Python, I get some programming languages out. So, it's got the feel for things. You could make arguments about, is that precisely the nearest match? Could I think of better words that would match? Yeah, probably. And if I trained it on a different set of documents, if I trained it purely on Computer Weekly, or I can train it on the output of the Strata conference, I'd probably get something much more precise. But here, this is on Google News, so this is what people talk about in the same kind of context as they talk about Hadoop or Python. If you're using this particular set of vectors, it's case sensitive. So you might want to be careful about that. So if I chuck in, you'll notice there aren't any snakes, basically, down here. If I chuck in Python with a small p, I start getting some snakes. Because just the number of times that you start a sentence with Python, when you're not talking about the language, but you're talking about the kind of snake, is very seldom. Therefore, capital P Python, it's always a computer language. Here's another one, Cassandra. So, either their market share isn't too great, or we've just got an overloaded word, right? We've got a word that appears in multiple different scenarios. So the number of female Cassandras occurring in Google News is much greater than the number of database Cassandras. You probably know the answer to this. Let's see if Google News knows the answer to this. So I'm going to say river plus London. What do I get? Shazam. After knocking off river and London, I get the River Thames. It's pretty cool. So I'm getting some understanding going on. I've got that association between riverness and Londonness that comes together in River Thames. And I haven't told it, I need you to classify rivers, and I need you to classify cities. This is just gone and done. For the tennis fans, so you may remember, you may have spotted it on the first slide, but what's the maths going to be in the kind of king, queen, that kind of thing? What's it going to be? How am I going to get the Spanish equivalent of Roger Federer? Yep.
Spanish.
Yeah, exactly. So does anyone know where Roger Federer is from?
Switzerland.
Bang on. So, if I ask for Federer less Swiss plus Spanish, I get right from the duck, which is a pretty good answer. I also get... The 5, that's just saying, please bring back only 5 results, the top 5. So that's just saying, limit my search to the top 5. Yeah, sorry, I should have explained that earlier. So, those of you who've been in Dundee where I've given this talk before will recognise the next one. So, it works with people too. So, if I chuck in a name, we saw Cassandra earlier, so we can say, right, okay, what is Mark like? So Mark is most like Steve, apparently. So if I weren't a Mark, I would be a Steve. And then I'd be a Dave, and I'd be a Greg, and a Mike, and a Chris, and all of these. Right, so this is what Marks are like. It's Christine. So if Mark were into Mark, he would be a Christine. So the kind of accident of birth, this is how it goes. Okay, so this is all good fun. I said I'd talk about fast text. So fast text is new last year. Rather than taking the whole word in one go, it chunks the words up into sets of characters. So n-grams or n charts. So it'll take little chunks and find the similarity in there. So Python has let's say it did it in 3-letter chunks, it would have a pint and a if and a tho and a hon, you know. What that allows it to do is cope with words it hasn't seen before and misspellings. So we all know if you take a stack of text this big, there's going to be misspellings in there. There's going to be things that aren't quite right. Or I might be able to reinterpret my misspellings. I might be able to ask for a misspelling and still get out the words that it should be. And if you've been on things like eBay, eBay copes with sort of misspelled searches and will bring you back things. This is the kind of concept that you might be really interested in. It's not just finding the precisely written words, but actually how do people write this in real life. Yeah. Finding new words is particularly of interest. So you're not quite as tied to your historic text as you were, or the precise phrasing of words. It can have a decent go at, well, this shares a lot of letters. This brand new phrasing of this word, doesn't matter I haven't seen it before, it shares so much in common with these other ones, I'm going to have a punt. Now, you know, take this with a pinch of salt. It might have a completely wrong punt, because it's never seen it before, but it could still be a massive amount of value. So, to finish up, I'm going to show you something where we've used this in the real world. So this was about job adverts. So a big pile of short descriptions of jobs on a job search site. So have a title, you know, that might say Python programmer. Or it might say, exciting new vacancy for person in High Wycombe. And, thank you, right, what's the job for? And then it'll have a little bit of a paragraph of text as well on what's the job about. And what we're trying to do is find, well, what is the job that it's talking about, really, in order to classify them into sector, and also to find out other things, so seniority. Because when you're trying to slice these things up, there's a whole bunch of different dimensions on which you could slice. So I could say, do I want to bundle senior managers and senior project managers together? Or do I want to bundle junior project managers and regular, you know, senior project managers together, and junior managers and senior managers together? So I can slice this in lots of ways. And in terms of which jobs are kind of relatively homogeneous with each other and which jobs are completely different from each other, this is what we're trying to disentangle. So for this example, we use the same Google News, the same top slice, just for sort of for speed. We lose some of the rarer words, but you know, this lets us get something out quickly. And we're going to show it in a picture. Now, these vectors are 300 dimensions long. That's quite hard to look at. in a picture. So we've squidged it down, to use a technical term, using an algorithm called TSNE. Go and look it up. And that brings it down into 2 dimensions for us. I'll show you the picture of how things look, and that was the method. You can read about that later. Can you see a bit of colour on this? There's lots of little dots on here. The physical representation, think of these like those vectors that we saw on the charts before. So proximity should indicate similarity to some extent. The colours are our sort of priors on which sector these jobs might be in. So we can see some places where colours are spread all over the map, and there are some where you've got little clusters of colour, which suggests that where they're clustered together, that means that our machine kind of clustering, our machine similarity, has matched up in some way with the human classification of similarity. So we can go and start having a little look around at some of these and have a look and go, well, look, is it working? Basically, is it doing what we're doing? Are we spotting meaningful clusters of stuff? So we'll start having a look up here. So there's a little sort of teal-coloured zone. So let's have a little look and see what these are. So that one that I'm hovering over there, that's a junior sous chef. So a chef. The one next to it is a chef de partie. The one next to that over there is a catering assistant. So, hurrah, we appear to have found a bunch of chefs and catering people. So let's move on, let's look at another section. There's a big wodge of orange and blue up here. They seem to be quite intermingled. So let's have a look and see what they are. So over there we've got a nurse, so a hospital nurse. Move along a bit. That's a care assistant. So we can see similarity. We've got caring, medical caring going on in that zone. What happens if we carry on over a bit? So that's a sort of nurse, but it's a different kind of nurse. It's somebody who works in a nursery, as in a sort of childcare assistant. If I keep going, I've got primary school teachers. So I've got this kind of continuation, of a continuum of care and then through nursing, the different types of nursing through to the education. So this is interesting, and we can see that these were not necessarily things that were easily split by the human classifiers. That we've got mixtures in and amongst themselves where they are actually pretty similar, but somebody's had to choose one or the other. This little cluster over there, barely, it's almost hidden by the big cursor. The link for those, it's this. It's where basically they didn't put in a description. Somebody just hit enter, and it came out as /n, which is like the new line for the thing when the text processing works. So these are all the people who didn't put anything in. Yeah, we also find in this picture there's the shouty adverts, so the ones where they're all written in all caps, really aggressive, and ones that used a particular kind of bullet point that kind of made it through the text cleaning. So, as with all good visualizations, the first thing you find is where your data is rubbish. So, you take this out, show me, tell me how these things are similar, and then I'll see why my data is poor. We've been talking about text all this time. This doesn't need to just be text. So, this is actually about patterns. When we're thinking about this, and I didn't go into the precise way about how it draws out the context, but what it's looking at is either feeding in the words around the word in question. So if I say this is a Python and it is green, I'll take the words all around Python, maybe 3 either side, 2 either side, something like that, feed that into the model and see what comes out at the end. And I'm going to compare that to what I previously thought of as Python and rinse and repeat. Or it goes the other way around. There's 2 flavors of models where I feed the one word in and then I try and get the model to work out what's going to be around it. So we can see actually this is going to work for a whole bunch of other stuff that comes in a pattern. If it comes in a sequence, then I can start to say, well, okay, if I've got this position, you know, I've got, let's say, yeah, playlists. So if I've got, you know, this Taylor Swift song here, what's likely that people will have put with that, near that, aside from that? If you like that, you'll like this kind of scenarios, particularly when there's ordering as well. So you can do that generic bucketed association, but we can get orders as well. And so there are lots of other vec things spinning up. So these are all our Python packages. So biological sequence, protein, gene, blah, blah, blah. You can see the application can go wider than just words. Just to clarify, this isn't, it might be conceptually deep, this is not deep learning. There's not lots of sort of hidden non-linear transformations within the neural network. The word2vec folks went for speed over complexity. They went for, if I make it fast, you can shove in loads and loads of text rather than just quite a lot of text. And this data over complexity thing. So it's not deep learning, it's just kind of quite cool. And that's that. So I hope I've given you a bit of a taster of how converting our words into a numeric space, this kind of vector representation, lets us look for similarity, lets us look for differences, and then lets us do neat things in the vector space around adding up and subtracting. We've got a mixture here. I mean, it's interesting, we talk about meaning and we talk about context. There's actually a bit of a mix-up between common usage and what it really means. I mean, and these blend massively, and linguistically there's a kind of massive debates to be had about, you know, is that really meaning, or is this just how it's used? In most cases, for us, we don't care. That if it's used like that enough, that probably means it'll do. The question is then about enough. How much data do I need to feed in? How precisely calibrated to my question set do I need the input data to be for this to be good? And that's the last point here, is that if you want to use this in anger, get to know your input data. Will it have the specialist stuff you need? Will it have the shortenings of the word? Will it be from the right area of the country, from the right country? Will it use the right terminology? And if it won't, is there a data set you can use? Can you train your own? The bigger the better, with all of these things. So, yeah, that's all I had to say. There's a few links at the end of the pack here to say thank you, and the papers, if you're into that sort of thing. You can read all the academics. Some of them are quite accessible, some of them aren't. And have a look, and more importantly, have a play, because it's just a case of downloading a couple of packages, downloading a couple of pre-trained vectors, and have a go. So, that's all I had to say. I hope you enjoyed it.